Hey there! In this video, we'll be looking at Boyle's Law, what it is, how we use it, and go over a few practice problems. First, let's start off with a definition. In summary, Boyle's Law states that pressure and volume of a gas are inversely proportional. This means that if pressure were to go up, volume would go down. And if volume were to go up, pressure would go down, right? It kind of do the opposite of each other. They are inversely proportional. Boyle's law makes this assumption while assuming that N and T are both constant. N refers to moles, or the number of molecules. Number of molecules. That must remain constant for this inverse proportion to happen. And temperature must also be constant. Right? So it's assuming that when the number of molecules are constant along with temperature, pressure and volume will then be inversely proportional. And if you want to look at a graphical representation of this, this is what it would look like. It would have an inverse shape, volume versus pressure, and this is a graphical representation of that. And if you wanted to linearize the data, if you wanted to make it so that it was a kind of a straight line, you can do something similar. So you could have volume here, and then 1 over pressure over here, because as again it is a inverse relationship, and in this instance this curve over here that depicts a inverse relationship, we can make that a direct relationship because this axis is already going to be inversed, so pretty straight line. This would be the linearized form with 1 over p at the x-axis. All right, and the way that I like to think about Boyle's law is to use an example. And the example I like to use is with a syringe, right? This is a syringe. And you may see this often. It's one of those things that they put COVID vaccines into. And I think it's a great way of visualizing Boyle's law, and it just kind of intuitively makes sense. So once again, Boyle's law suggests that pressure and volume are inversely proportionate. Now, if you were to squeeze on this syringe, put pressure into it, go all the way in, this is what it would look like. So this is the before. Right? This is the before, and this is the after. All right, and so here's a sample of gas. Sample of gas is represented by these red dots, and this is the force being applied. So initially, there is quite a bit of volume here, right? In this box over here, there's quite a bit of volume, and after, what happens is once this force comes down, right, the volume is decreased, but the pressure is increased here. Because pressure, as we mentioned in an earlier video, pressure is defined by how often these little dots hit the surface of the container, right? How often the molecules collide with the container, the pressure exerted on the container of gas. All right, so as the volume decreases, these gases are moving at the same rate, but they're hitting the outside of this container more and more often, increasing the pressure, right? So that is a good way to visualize this inverse relationship. In this example, you see that as volume goes down, pressure goes up, and it works vice versa as well. If you were to bring this back up, right, from this position, if you were to bring it back up again, there's more space for the molecules, and they won't hit the side of the container as often. So in this instance, volume goes up and pressure goes down. All right, so that is the way I like to visualize Boyle's law in action. And it's a good way to kind of intuitively know it as opposed to memorizing relationships. Now, we did just explore a proportion. Well, our proportion was that volume is going to be inversely proportionate to 1 over p. Now, although proportions are usually really cool, this in itself won't be able to do much when it comes to calculations. What we need to do is get an equation. And the way we get an equation from a proportion is we add a constant value, which we're going to represent by k. All right, so we're just going to insert this constant value into the proportion to make it an equation. So that means that v is going to be equal to k into 1 over p. All right, now we have some kind of equation. Now we can play around with this a bit more. If we were to multiply both sides by p, right, you get p over here, that equals 1, so it's going to be k, but you get pv over here, so it's going to be pv equals k. So this is what this proportion simplifies to. Now, the application of Boyle's law comes down to this expression over here. Imagine I have a sample of gas at a given set of temperature, like say P1 and V1, right? One pressure, one volume, and then it changes to a different set of conditions. So P2 and V2, right? Both of these are going to equal that constant value, right? If it's the same amount of gas at the same temperature, they're both going to be equal to this constant value, even though the pressure and the volume has changed, because this is the constant value. So what you can end up doing here is that for that given sample of mass, since they're both equal to K, you can equate both these expressions to each other. So that would be like P1 V1 is equal to P2 V2. All right, so that is the equation that is associated with Boyle's law, and that is where it comes from. I find this to be pretty important because me personally, I've kind of wondered why, what does this relationship have anything to do with the inverse relationship? Why is it in multiplication? Shouldn't it be, in division or something? So this is kind of how that whole thing comes to be, how you can use constants to equate the equations to each other. And this is the equation that you'll be using in chemistry for Boyle's law, this one right over here. And this is where we'll be doing all of our calculations. And we'll get to those calculations right now. Okay, practice problem number 1. Mark takes a sample of argon from Mars in a 4-liter container with a pressure of 184 kilopascals. NASA tells Mark to lower the sample's volume to 2.5 liters. What is the pressure of the gas? All right, so this is a reference to The Martian, the book and the movie. Main character is Mark there. And we can use this information to set up Boyle's law, the equation that we derived here earlier, right? So the first thing I like to do when it comes to gas problems is write out what we have given to us. All right, so what we have given to us here is the initial volume, 4 liters of the container, right? So that's going to be V1. Remember that V1 is always going to be the initial. So whatever one subscriptor is, that's the initial. So V1 equals 4 liters. And we know that the initial pressure is 184 kilopascals. So P1 is going to equal 184 kilopascals, kPa, right? And we know one more thing. We know that NASA tells Mark to lower the sample's volume to 2.5 liters. What that means is that that's the new set of conditions. Remember over here when we derived that equation, we assumed a new set of conditions, a new volume, a new pressure. That is what that is. So this is going to be it's going to be V2 because this is a new volume, right? Since it's in liters, it refers to lowering the sample's volume. It's going to be 2.5 liters. And they're asking for the pressure of the gas now that it's in a 2.5 liter container. So they're asking for P2. That is the question mark. Okay, so the way I like to do this is by rearranging the equation before I put in the numbers. This is a matter of preference. It's not the end of the world if you do it differently. I find it a lot more easy, a lot more simple, and a lot more clean. So this is the equation that we have, and obviously, as you can see, this relates to all of the variables. So we use the right equation. And we're trying to isolate for P2, or we're trying to solve for P2. And the easiest way to do this is if we divide both sides by V2, right? And divide it, you'll get 1 here, and you can divide it on here. So P2 is going to equal P1 V1 over V2. All right. Now what we can do is we can use these given values and substitute that into the equation. All right, and I'm just going to work horizontally from here because the next question I didn't give too much space, but you feel free to work vertically as well. So what we have here, P1 is going to equal 184 kilopascals. Here you have V1 being 4 liters, right? And that's going to go over the value for V2, which is going to be 2.5 liters. All right, so what we do here, we do some math. The units cancel out, so your final answer is going to be in kilopascals, which is great because we're actually looking for pressure. So that means you did it correctly. 184 times 4 divided by 2.5, that should give you about 294.4 kilopascals. All right. And if you wanted to consider significant figures, you have one significant figure over here. So that's just going to be 300 kilopascals. All right, so hopefully that made sense. Let's try one more question for good measure. Okay, in this question, its balloon has an internal pressure of 107 kilopascals, and a volume of 2.9 liters. However, Richie tries to break it, and the pressure of the balloon increases to 127 kilopascals. What is the new volume of the balloon? All right, so this is an obvious reference to the movie It, and Rishi is one of the kids in the movie from my memory. And that's not significant. The significant part here is to start with the solving the question. So you can take some time, pause the video, and try to see if you can solve it yourself. And I'll go over it right now. So the first thing you want to do, as we did in the last video, is sort out our given values. So we know that its balloon initially has a pressure of 107 kilopascals. Initially is a huge key term here. If it was there, you would use that term initially. That's a great indicator of what the first value is, but in this instance, it's pretty obvious anyways. So it's going to be P1 is going to equal 107 kilopascals. That's like the internal temperature before anything happens to it. And the volume, V1, is going to equal 2.9 liters, right? However, when Rishi does his tries to break the balloon, the pressure increases to 127 kilopascals. So that means that's a change, and that's a new set of conditions. So it's going to be P2 is going to equal 127 kilopascals. And we're trying to solve for the new volume, which is going to be V2. All right, so V2 is going to be our unknown. We're trying to solve for V2. So same thing we did in the last question. I'm just going to write out the expression and then solve for V2. Try to get it by itself. That makes it a lot easier in my eyes. But you can put in numbers right now and rearrange it. It doesn't really make too much of a difference. So what we do here is you want to solve for V2. You're going to divide both sides by P2, right? Because then P2 is what cancels out here, leaving V2 by itself. So you're going to get V2 is going to equal V1 P1 over P2. All right. Now we can substitute the values in from above. And we know that V2 is going to equal V1 was 2.9 liters. P1 is 107 kilopascals. And P2 is 127 kilopascals. All right. Now, if we check the units just to make sure, you're going to see that our final units are going to be in liters, which means yes, it is appropriate for volume. We set this equation up correctly, and then 2.9 times 107 divided by 127 should give you about 2.4 liters, right? So V2 is equal to 2.4 liters. And if you ever want to double check your work, you can kind of use intuitive common sense as well, just to understand. So the pressure of the balloon increased, right? That means the volume is going to decrease because they're inversely proportionate. So pressure increased. Initial volume was 2.9. Now it's 2.4. So it did decrease. So that makes sense. And just going back to the first problem as well, the volume was decreased, so that means the pressure had to increase. The initial pressure was 184, final pressure was about 300. So as we can see, these answers also make intuitive sense with the proportion that we looked at earlier. All right, so in this video, we looked at Boyle's Law, what it is. We went from the proportion to the equation. We looked at how we can remember Boyle's Law with examples. And finally, we looked at some practice problems where we can apply the equation. If you enjoyed this video, if you found it helpful, please click the subscribe button, consider liking the video, and I hope to see you guys in future videos as well.